Welcome to the deep dive. Today, we're tackling a truly unique element, plutonium.
Yeah, definitely unique.
We've got a fascinating collection of research compiled here, all zeroing in on this one substance. We're going to unpack everything from how you get it out of its compounds to its physical quirks, how to purify it.
Its relationships with other metals, like cerium and zinc.
Right, those phase diagrams, and even, looking at its microscopic structure.
And what makes this particular deep dive so interesting, I think, is the historical lens, our sources, their proceedings from a symposium way back in 1959.
1959, so like over 6 decades ago.
Exactly. It gives us this remarkable opportunity to see how scientists understood plutonium then, before a lot of the tech and theories we use today even existed.
It's like stepping back in time, but for nuclear materials science.
Pretty much, yeah.
Absolutely. So our mission today for you, the listener, is to kind of pull out the most compelling and maybe surprising insights about plutonium metallurgy from this historical snapshot.
Right. Give you a solid understanding without getting too bogged down in the weeds.
Exactly. We want the key aspects. Prepare to have your perception of this element shifted. It's a bit of a wild ride.
It really is.
Okay, so let's get right into it. What were some of the fundamental challenges? What were scientists grappling with when they first tried to understand and work with plutonium?
Well, the book itself kicks off by saying, look, the metallurgy of plutonium was pretty new in '59. Only about 15 years of serious research under its belt.
15 years, that's not long in scientific terms.
Not at all. And right from the start, it presented, and honestly, it still presents some incredibly unique and complex hurdles.
Unique seems like a massive understatement thinking about what they were dealing with. Just handling it, that sounds incredibly difficult.
It was and is. The extreme radioactivity and, frankly, the toxicity of plutonium meant every single operation, everything, had to be done inside these hermetically sealed glove boxes.
Right, like working through thick gloves behind glass.
Exactly. Imagine trying to do delicate metallurgical experiments like that. It inherently limited the scale, too. They were typically dealing with tiny amounts of material.
So big industrial processes like you'd normally think of were just off the table.
Pretty much, yeah. Especially back then.
Right. That puts things in perspective. But it gets even more intricate, doesn't it? Something about its fundamental structure.
Oh, yeah. Plutonium is infamous for its allotropy.
Allotropy. That means it changes form, right?
Changes form dramatically. Between room temperature and its melting point, about 639 Celsius, it morphs through no fewer than 6 distinct crystal structures.
6. Wow.
Yeah, 6. Each one with his own density, its own properties. This constant shifting with just, relatively small temperature changes has huge implications for mechanical property.
Like trying to build a house on shifting sands.
That's a pretty good analogy, actually. Imagine trying to design a component when the material itself keeps changing its basic structure. It made predicting and controlling its behavior during processing incredibly challenging.
Okay, that sounds nightmarish. And then on top of all that, there was the secrecy issue, wasn't there? That must have slowed things down.
Precisely. The whole Cold War context meant tons of research was classified. It severely restricted how information was shared, hindered that open scientific back and forth.
So the people working on it were really pioneers, figuring things out under pretty tight constraints?
Absolutely. Navigating complex problems with limited information sharing. So, okay, we know it was tough. How do they actually make plutonium metal in the first place?
Yeah, that's the million-dollar question, isn't it? The research outlined several different paths for converting plutonium salts into the metal form. It mentions heating compounds like oxides and halides with reducing agents, things like hydrogen or carbon. But it sounds like those methods had their own problems.
They did. Those thermal decomposition routes often needed incredibly high temperatures. We're talking over 3,000 degrees C sometimes just to reduce the oxide. Yeah. And the other idea, using plutonium amalgam, dissolving it in mercury, well, that brought the risk of contaminating the final product with mercury. Nobody wants that.
No, definitely not. What about electricity? Did they try electrolytic methods?
They looked into it, yeah. But generally, those suffered from poor efficiency, low current yields, and the metal often formed as these little inconvenient globules instead of a nice solid chunk.
So, not ideal. What was the more reliable approach then? What actually worked consistently?
The research really points toward reduction using alkali or alkaline earth metals. Calcium specifically comes up a lot as a common and relatively simple technique.
Calcium, okay.
Yeah, using calcium to reduce plutonium halogens, the fluoride or chloride or even the dioxide, the oxide form. A big plus was that calcium metal itself could be obtained relatively pure and was easier to handle than some alternatives.
Okay, let's dig into this calcium reduction a bit more. How did it work practically, say, with the oxide?
Right. For the oxide route, you'd basically mix plutonium dioxide, PuO2, really well with calcium metal powder. Then you heat it up quite hot.
And the calcium just takes the oxygen.
Essentially, yeah. Calcium is more reactive with oxygen, so it steals the oxygen atoms from the plutonium, leaving you with metallic plutonium. But
there's always a but.
There's always a but. It also formed a slag, a byproduct, calcium oxide in this case. And the efficiency, how much plutonium you actually recovered, could vary depending on how much you were trying to make. The source mentioned something like 92% efficiency at a small 25 milligram scale.
Only 92%. What made getting that last 8% so tough? Was it separating it from the slag?
Exactly. Getting that really fine metallic plutonium fully separated from the calcium oxide slag, especially if you scaled it up, that was a big challenge for maximizing the yield.
Interesting. Okay, what about the other main route you mentioned, the fluoride route? The research details this whole multi-stage thing involving oxalate.
Yeah, the fluoride route was definitely a key method for getting high-purity plutonium metal. It was a bit more involved, though.
How so?
Typically, it started by precipitating plutonium oxalate from a solution, usually a nitrate solution. Think of it like selectively grabbing the plutonium ions out.
Okay.
This oxalate powder would then be carefully dried and heated calcined to turn it into plutonium oxide.
Back to the oxide.
Temporarily.
Yeah.
Then that oxide would be reacted with hydrogen fluoride gas and hydrous HF to make plutonium tetrafluoride, PF4.
Right.
And finally, this PF4 powder would be mixed with chunks of calcium metal inside a crucible, sealed up, and heated in a furnace.
And the calcium does its thing again.
Yep. Calcium reduces the plutonium fluoride to plutonium metal, and you get calcium fluoride slag this time. Figure 1 in our source actually has a nice little flow chart showing this whole sequence.
So quite a chemical dance to get to the metal. Now, the text also spends a good chunk of time on work done at Los Alamos back in the 40s. What was their specific angle with this calcium reduction?
Yeah, and the Los Alamos work in the 40s was laser-focused. Their goal was developing reliable methods to produce high-purity plutonium metal, specifically for what the source calls bomb reduction.
Ah, okay. For weapons applications.
That was the context, yes. They did a lot of work on reducing both plutonium trichloride, BCl3, and the tetrafluoride, PF4, using calcium.
And how did they contain the reaction?
They used these sealed steel vessels, which they actually called bombs. These bombs were lined with a refractory material, usually magnesium oxide magnesia, to stop the molten plutonium reacting with the steel walls at the high temperatures involved.
A bomb lined with magnesia sounds intense, like trying to contain a mini volcano or something.
It kind of was. Figures 1 and 2 in that section show drawings of these bombs and the different liners they used for different amounts of material.
You mentioned magnesium oxide, magnesia. Did they add anything else to the mix? The text mentions iodine sometime.
Good catch. Yeah, in some cases they'd add a little bit of iodine into the reaction mix. They called it a booster.
A booster. What did it boost?
It likely helped kickstart the reduction reaction more effectively. And it could potentially improve both the final yield and maybe even the purity of the plutonium metal.
Interesting trick. And they weren't just doing this with tiny amounts, right? You said Los Alamos scaled this up.
Oh, absolutely. Their research showed this calcium reduction method worked well at scales from just a few grams right up to kilograms of plutonium per batch.
Kilograms? Wow.
And the purity.
They reported typical yields with purity over 99% by weight. Table 3 in the source actually breaks down the best conditions they figured out for different scales using both the chloride and the fluoride starting materials.
That's remarkably clean, especially given all the challenges we talked about earlier. What kinds of impurities were typically left behind, even in trace amounts?
Table V gives a pretty detailed list. You'd find traces of lighter elements, lithium, beryllium, boron, also some common metals like sodium, magnesium, aluminum, potassium, calcium itself, iron, manganese.
And non-metals like carbon, oxygen, silicon were in there too, in small amounts. But despite all those trace bits, the overall plutonium purity was consistently better than 99.8% by weight.
Still, incredibly pure, all things considered. So they've made this high-purity metal. Now, how did they actually look at it? Examine its properties, especially its microstructure. That's where metallography comes in, right?
Exactly. And again, because it's plutonium radioactive, toxic preparing and examining samples for metallography needed highly specialized techniques. And guess where it all happened?
Back in the glove boxes.
Back in the glove boxes.
Yeah.
Figures 1 and 2 in that section show examples of these really complex glove box setups designed just for metallographic prep. Imagine trying to polish a tiny metal sample perfectly through those thick gloves.
It sounds like building a ship in a bottle, but way more dangerous. What did the prep process involve?
Usually it started with carefully mounting a small piece of the plutonium metal in a block of plastic. Just makes it easier and safer to handle. Then came the really meticulous part. Mechanical polishing. Using finer and finer abrasive papers, then diamond paste, to get an absolutely smooth mirror-like surface. No scratches allowed.
Okay.
And often the final step was electrolytic polishing. Using an electric current in a special solution to gently etch the surface. That's what reveals the underlying grain structure, the different phases within the metal.
Ah, the etching brings out the details. The source even mentions the lubricants they used during polishing.
Yeah, the details mattered. Every step was carefully controlled.
And then how did they actually see the structure they'd revealed?
They used specialized metallographic microscopes, which were also inside glove boxes.
Of course they were.
Naturally. These microscopes let them study the size and shape of the individual crystal grains, how they were arranged, and identify any different phases present in the metal or its alloys. Figure 3 actually shows one of these micrographs, a photo taken through the scope of a plutonium sample. You can clearly see its intricate microstructure.
It's just astounding, the level of care and complexity needed just to look at a tiny piece of this stuff.
Okay, so the conversation in our sources then shifts towards alloys.
Yeah.
Plutonium mixed with other metals, and these roadmaps you mentioned earlier, phase diagrams. Explain those for us.
Right. Phase diagrams. Think of them as essential graphical maps. They tell you exactly which phases, solid, liquid, maybe a mix, are stable when you combine plutonium with another metal.
Stable at different temperatures and different mixing ratios.
Exactly. Different temperatures and compositions. They're absolutely crucial for understanding how plutonium behaves when you alloy it and for designing alloys that have specific properties you want.
So like a recipe book for metal mixtures, showing what you get at different ingredient ratios and cooking temperatures.
That's a great way to put it. A recipe book for metals.
Okay, cool. Let's look at one then. The plutonium-cerium phase diagram, figure 1 in that section. What jumps out from that map?
One of the really significant things in the PC system is the extensive solid solubility of cerium in delta plutonium. Delta plutonium, that's one of the 6 forms, right?
Yep, one of the higher temperature solid forms.
Yeah.
An extensive solid solubility means you can dissolve a whole lot of cerium atoms into the crystal structure of delta plutonium, and it still stays as one single uniform solid phase over quite a wide range of temperatures and compositions too.
Okay, so they mix well in that specific state. What else does the diagram show?
It also shows several intermetallic phases forming. These are like distinct chemical compounds, specific ratios of Pu and C atoms bonded together. You see things like the epsilon phase and a region marked delta plus beta C, meaning a mixture of those 2 solid phases.
Interesting. Any other key features?
Yeah, there's a eutectic reaction marked at 625 Celsius.
Eutectic. Sounds technical.
It just means there's a specific mixture composition that melts at a lower temperature than either pure plutonium or pure cerium. And when that specific liquid mixture cools, it solidifies directly into a very fine mix of 2 solid phases, almost like a microscopic layer cake structure.
Huh. A sweet spot for melting. So these diagrams pack in a ton of information. How on earth did they figure all this out back in 1959? Must have been painstaking work.
Oh, incredibly painstaking. It involved combining results from several different experimental techniques.
Like what?
Things like thermal analysis, carefully heating and cooling alloys, and precisely monitoring temperature changes. Those changes signal when phases transform. Also dilatometry.
Dilatometry.
Measuring tiny changes in the material's volume or length as you change the temperature. That also reveals transformations. Then there was X-ray diffraction to identify the actual crystal structures of the phases.
Okay.
And of course, metallography, like we just discussed. Visually examining the microstructures of alloys quenched from different temperatures to see directly which phases were present.
Wow. A real combination of tools.
Yeah.
Okay, let's switch gears to the other example diagram, plutonium-zinc. Also figure 1. How does this pairing look different?
The Pu-Zin system behaves quite differently from Pu-Si. Here, the big thing is the formation of 4 distinct intermetallic compounds. Pu-Zin-2, Pu-Zin-3, Pu-Zin-8, and Pu-Zin-17. Lots of specific compounds.
4 distinct ones. Okay.
Yeah. And another practical issue with zinc is its relatively high vapor pressure at high temperatures.
Meaning it likes to evaporate easily when hot.
Exactly. Which made preparing these alloys tricky, because the zinc could just boil off while they were trying to melt and mix things.
That sounds like a headache. What about solubility? Does zinc dissolve well in plutonium like cerium did?
Much less so. The diagram shows the solid solubility of zinc and plutonium is pretty limited. Zinc doesn't really like to dissolve into the plutonium crystal structure to form those single-phase solid solutions we saw with cerium.
So they prefer to form those specific compounds rather than just mixing together. The text also mentions a bunch of micrographs for Cousin, figures 2 to 10. What do those pictures add?
Those micrographs are really valuable visual proof. They confirm the existence of the different phases and structures that the phase diagram predicts for different zinc concentrations.
So you can actually see the different compounds.
Yeah, you might see, say, distinct crystals of Puzin-2 embedded in a matrix of another phase. It helps verify the diagram and understand how the alloy actually solidified and looks on a microscopic level.
Seeing is believing, especially with something this complex. Okay, so zooming out from these specific examples, what are the big takeaways? What general principles govern plutonium's alloying behavior?
Well, a few key things emerge. First, as we keep saying, those 6 allotropic forms of plutonium are fundamental. They massively influence how it alloys. The phase diagrams are basically maps of how those different Pu structures interact with other elements.
Right, the shifting sands again.
Exactly. Second, plutonium's position in the periodic table and its electronic structures, specifically those tricky 5L electrons, are critical.
Ah, the 5 electrons. They always seem to be involved in actinide weirdness.
They really are. They're kind of loosely held and can participate in bonding in complex ways. That contributes a lot to its very complicated alloying properties. Figure 1 in the alloying behavior section actually shows a periodic table highlighting all the different elements they'd tried alloying with plutonium by 1959. It's quite a range.
Those 5 electrons sound like trouble. The text also brings up something called Dark-Nguri maps. What are those about?
Dark-Nguri maps, shown in figures 2 and 3 of that section, are pretty clever graphical tools. They try to predict how much solid solubility you might expect between 2 metals.
Predict solubility. How?
They plot elements based on 2 fundamental properties, atomic size and electronegativity, basically, how strongly an atom attracts electrons.
Okay.
And for a given form of plutonium, like delta Po, there's an elliptical region drawn on the map. Elements whose size and electronegativity fall inside or close to that ellipse are predicted to be good candidates for forming extensive solid solutions with delta plutonium.
So it's a predictive shortcut based on basic atomic properties.
Pretty much, yeah. A way to make educated guesses about which combinations might work well.
That's quite ingenious for the time. Okay, lastly, the text briefly mentions liquid immiscibility and intermetallic compounds as other important factors. Quick summary.
Sure. Liquid immiscibility is just when 2 molten metals won't mix properly, like oil and water. They form separate liquid layers. This can happen in some plutonium alloy systems, often influenced by differences in electronegativity and electron structure.
Okay. And intermetallics.
Intermetallic compounds are what we saw clearly in the Puzin system, those distinct phases like Puzin-2. They have unique crystal structures and often very different properties from the original metals. Their formation is also tied to factors like electronegativity differences and how the atoms prefer to bond.
Fascinating stuff. Okay, so to kind of wrap this all up, we've really dived deep into plutonium metallurgy as they understood it back in 1959.
We have.
We've looked at the huge challenges, the radioactivity, toxicity, those 6 shifting forms.
The ingenuity in making the metal, like that calcium reduction method.
Right, the specialized, super careful techniques needed just to look at it under a microscope.
And then the complex ways it behaves when mixed with other metals mapped out in those intricate phase diagrams for things like cerium and zinc.
Yeah.
It's just abundantly clear, isn't it? Even in those early days, plutonium was this uniquely demanding but also captivating field of study.
Absolutely. That inherent radioactivity, the toxicity, and those complex solid-state changes really set it apart.
Truly an element unlike almost any other.
So, as we bring this deep dive to a close, here's a final thought for you, the listener, to mull over. Thinking about that 1959 context where the understanding of atomic behavior was still evolving rapidly, what future breakthroughs might totally change how we understand and work with complex elements like plutonium? Like advanced computing, maybe, or deeper quantum insights.
Exactly. Could those lead to discovering entirely new plutonium alloys? Alloys with properties we can't even predict today?
It really makes you think about how much science continues to evolve, doesn't it? Often
Yeah.
in surprising ways. It certainly does. Well, thanks for joining us on this deep dive into the world of plutonium metallurgy.